Hi listeners, you are welcome to the continuation of our physics tutorial class from your favorite student ScoreBooster, your online tutorial provider on JAMB, WAEC, NECO and NAPTIP exams. Today's presentation shall be on Workdone. My name is Bangbade A. Now, before we continue, we need to consider the learning outcomes for this particular presentation, which goes thus. At the end of this presentation, listeners should be able to define work done. They should also be able to state the formula for work done. Listeners should also be able to relate work done to energy. And lastly, they should be able to solve relevant UTME questions relating to work done. Now, on to work done. Work is done when a force moves a body across a distance in the direction of a force. I repeat, work is done when a force moves a body across a certain distance in the direction of a force. By work done itself, it's actually the product of the force and the displacement. And if you can recollect from our video 1, that is on linear motion, we define displacement as a distance in a specified direction. So work done is a product of the force and the displacement. Mathematically, work done, that is WD, equals force times distance. But in the presence of angle theta, that is angle of inclination of the force, our work done will be F cos theta times D, where there is a distance. But in the absence of theta, then work done will be force times distance. Now, having understood the meaning of work done, the next thing to consider is the work energy conversion. I mean, the interconversion of work and energy. Now, if the work done on a body is all utilized in setting it in motion, then work done will be equal to change in the kinetic energy. Of course, kinetic energy is the energy in motion, energy that sets an object in motion. That was discussed in video 8. I urge you to please refer to that for the necessary foundation. But here now, if the work on the body is all utilized in setting the body in motion, then work done equals change in kinetic energy. Similarly, the work done may be equal to other forms of energy, such as the electrical energy, heat energy, etc. So that is to say, the work done can be converted into other forms of other energy, such as electrical energy, heat energy. So we can also calculate work done from the parameters of this energy. Now, the next term we will be considering is the electrical energy E calculation. I mean the calculation of electrical energy E. And we have about 3 different formulas for this term. The first is E, electrical energy equals I-T. E equals I-T. But from Ohm's law, we have Phi equals IR. That is, potential difference is equal to current times resistance. Then we substitute for phi in place. If we substitute IR in place of phi in the formula E equals I phi t, then we have E equals I times, in place of phi now we have IR, then times t. So I times R will give us I square, then RT. So we have E equals I square RT, which is a derivative from the first formula, which says E equals I phi t. So E in this case is the energy in joule, I is current in ampere, R is resistance in ohm, T is time in seconds, while phi is potential difference in volts. Similarly, from the same Ohm's law that says phi equals IR, we can make I the subject of formula by dividing both sides by R, and that will give us I equals phi over R. I equals phi over R. So if we substitute for I in E equals I phi t, that will give us E equals, in place of I now we put phi over R, then times phi, then times t. So that will give us phi times phi is phi square. So we have phi square t over R, phi square t over R. So the three formulas are E equals I phi t. Then the second one is E equals I square RT. E equals I square RT. And the last is E equals phi square t over R, phi square t over R. E in this case is energy in joule, I is current in ampere, phi is potential difference in volts, t is time in seconds, R is resistance in ohm. So it is very important to take note of these formulas, as we may need them later in calculating the required electrical energy. Now on to UTME sample questions, and the first question we shall be considering comes from 1987 number 8, and the question goes thus: a constant force of a constant force of 40 Newton acting on a body initially at rest gives an acceleration of 0.1 meter per second square for 4 seconds. Calculate the work done by the force. You have the option A to be 8 joules, option B is 10 joule, option C is 32 joule, while option D is 160. Now to solution to this question. You have from the question we are given the force F to be 40 Newton, and since they said the object starts from rest, that means initial velocity u is 0. Then we are also given acceleration a to be 0.1 meter per second square, and time t to be 4 seconds. So the distance is not given a. We are to recall that work done is equal to force times distance, meaning that we need distance for us to be able to calculate work done from force. And here now, from the given parameters, which are u, a, t, then we can get x, which is distance s, and that was comprehensively exploited in video 1 on linear motion. So I urge you listeners to please refer to video 1 on linear motion for the details of these linear equations. But the suitable one for this question will be the equation connecting u, a, t and s, and that will be s equals ut plus half at square. Then when we substitute our s, will be u, which is 0, into t, which is 4, plus half into a, which is 0.1, then into t square, that will be 4 square. So our x will be 0 times 4 is 0 plus half into 0.1 times 4 square. 4 square is 16, so 0.1 times 16 will be 1.6. So eventually we have s equals 0 plus half into 1.6, and that will be s equals half of 1.6, which is 0.8 meter. So our s is 0.8 meter. Since we know our s now, distance s, then we can proceed to calculation of work done using the equation work done wd equals force times distance, that is f times s, and that will give us work done equals force, which is 40 newton, times x, which is 0.8 meter. So that will give us 32 joule, making option C the correct answer for this particular question. Now the next question we shall be considering comes from 2000, year 2000, number 1, and the question goes thus: a catapult used to hold a stone of mass 500 grams is extended by 20 centimeter with an applied force F. If the stone leaves with velocity of 40 meters per second, the value of the force F is dash. So we are given option A to be 4.0 times 10 raised to power 4 Newton. Option B is 4.0 times 10 raised to power 3 Newton. Option C is 2.0 times 10 raised to power 3 Newton. While option D is 4.0 times 10 raised to power 2 Newton. Now to solution. The first thing is to write out the given parameters, and from the question we are given mass m to be 500 gram. So that we need to convert that to kilogram by dividing it by 1000. That will give us 0.5 kilogram. And also you are given the distance to be 20 centimeter. So we also need to convert this to meter by dividing it by 100, and that will give us 0.2 meter. 0.2 meter. Then we are given the velocity to be 40 meter per second. Now, if we follow the law of conservation of energy, then the kinetic energy here can be equal to the work done. Kinetic energy Ke will be half mv square, and that will be equal to work done, which is force times distance. Therefore, we can say half mv square equals force times distance. So, in substituting for the parameters, we have half into m, which is 0.5 kilogram, then into v square, which is 40 square, will be equal to f, that is the force, times distance, which is 0.2. And if we solve that further, we get half into 0.5 into 40 square is 1600, which will now be equal to f times 0.2. So if you pick a calculator, half, or you cut, you can use 2 to cut 600. We get we use 2 to cut 1600 to get 800. So we'll be left with 0.5 times 800 on left hand side, which is equal to f times 0.2 on the right hand side. So 0.5 times 800 will give us 400, which is equal to force times 0.2. Then we can divide both sides by 0.2 to get f equals 400 over 0.2, and that will give us 2000. When we convert that to standard form, it will be f equals 2 times 10 raised to the power 3 Newton, making option C to be the correct answer for this question. Now the next question we shall be considering is question 3, which comes from 1995, number 44, and the question goes thus: an electric current of 2 ampere flows in a heating coil of resistance 50 ohms for 3 minutes 20 seconds. Determine the heat produced. So in this particular question, you are given option A to be 0.5 kilojoule, option B is 8.0 kilojoule, option C is 20.0 kilojoule, while option D is 40.0 kilojoule. Now on to solution. From the question, the first step is to write out the given parameters, and we are given current I to be 2 ampere, then resistance R to be 50 ohms. Then we are given time T to be 3 minutes 20 seconds. Of course, we need to convert that to seconds, being the standard unit for time. So 3 minutes will be 3 times 60 seconds, then plus the 20 seconds we are having. So 3 times 60 will be 180 seconds plus 20 seconds. That will give us 200 seconds. Now, from the parameters we are given, we have current I, resistance R, and time T. And equation, the formula for calculating energy connecting I, R, and T is E equals I square RT. So we will substitute for that. Our E will be I square, that is 2 square, into R, which is 50 ohms, then into T, which is 200 seconds. So our E will be 2 square is 4 times 50 times 200. That will be 4 times 50 is 200. Then 200 times 200 will give us 4000 joule. So if we convert that to kilojoule by dividing it by 1000, we have 40 kilojoule, making option D the correct answer for this question. Now on to practice question from the UTME, and the first question presented to you here comes from 1990 number 9, and the question goes thus: a stone of mass m kg is held h meter above the floor for 50 seconds. The work done in joules over this period is dash. So you have option A to be mH, option B to be mgh, option C to be mgh over 50, while option D is 0. The expected answer here is B, option B, that is mgh, and it follows the law of conservation of energy. Then the second question you are presented with here comes from 2004 number 42, and the question goes thus: a steady current of 2 ampere flows in a coil of EMF 12 volt for 0.4 seconds. A back EMF of 3 volt was induced during the period. The stored energy in the loop that was utilized is dash. So you have option A to be 7.2 joule, option B to be 12.0 joule, option C to be 2.4 joule, while option D is 9.6 joule. Expected answer here is A. Then you have the hints. Your phi here will be the total voltage minus back EMF. The total EMF minus back EMF, that will be 12 minus 3. Then you use the formula connecting I phi t, that is A equals I phi t, and the expected answer is option A. So we urge you to try this for your own practice. Now our next video will be on power, and with sample questions and solution from the UTME. I urge you to please subscribe to our YouTube channel, like and share our videos, as we promise to be bringing you more of this interesting presentation on subjects related to UTME. Thank you.